We're looking at Ceph. Let's check it out. All right. Ceph is distributed storage. It scales, I think, super big. I think you use it for if you're like a huge company. I don't know exactly what promises they make. Software. They expose block storage like a disk. They also expose like S3s, Amazon S3 style object storage. And they also have a Ceph file system, which is kind of like a maybe more up-to-date NFS. But the idea is you throw a bunch of drives at it, maybe a rack of drives. Don't do that. And let's see if we can find a picture of a rack. And it's just used for distributed storage. There have been other distributed storage solutions, and Ceph is one that's open source. Google has a few, and that's that. So we've got a diagram here. Cephmon is just some monitor, and the underlying technology, I think, is what they call Rados, a reliable, autonomous distributed object store comprised of self-healing, self-managing intelligent storage nodes. So you have a bunch of nodes that takes up a lot of CPU to figure out where to place each object. But basically, when you store a file, let's say in object storage, it breaks up the chunks. It stores it so that you have some amount of redundancy, like maybe you have 3 copies of each chunk. I don't know what the official word for a chunk is. But then when you retrieve it, I don't know exactly how that works, but you have some system for essentially routing that's configurable. And then on top of this Rados layer, they have these APIs, including librados, which I'm not really sure what it's about, but it says a library allowing to directly access Rados. That's probably for implementing other things. And then Rados gateway is what they call the S3 style storage. And RBD, I think, is the block storage for like if you want to have a VM or a database. And then Cephfs is the NFS style storage. But that all lives on top of Rados. So we're going to see what that's about. We're going to see it. We're going to check it out. And that's how it is. There's going to be way, way, way too much to look at. It's in C++ and Python and some TypeScript and whatever Raku is. I think that's maybe the Perl 4. Raku. Perl 6. Sorry, all the Perl fans out there. All right, so back to the Ceph source code. I guess we definitely want to see Rados, and that might be all we see. I feel like the S3 API is going to be relatively simple on top of that. The block API, maybe Cephfs, is probably going to be more complicated. We have crypto. Crush is the set of rules, I think, that define routing. I don't know what the acronym stands for. Does it tell us here? Crush. The crush is an algorithm, not a set of rules, but I think it occupies the same place. The crush algorithm computes storage locations in order to determine how to store and retrieve data. Crush allows Ceph clients to communicate with OSDs. These are the disk daemons. I think it's specifically the daemons and not the disks themselves. Directly rather than through a centralized server or broker. Okay, so it's not hitting some sort of reverse proxy. By using an algorithmically determined method of storing and retrieving data, Ceph avoids a single point of failure, a performance bottleneck, and a physical limit to its scalability. Okay. It uses a map of the cluster, the crush map, to map data to OSDs, distributing the data across the cluster in accordance with configured replication policy and failure domains. It contains a list of OSDs and a hierarchy of buckets, hosts, and racks, and rules that govern how crush replicates data within the cluster's pools, and it reflects the physical organization of the installation. Okay, so that's what Koorosh does. We'll see some of that. I hope. Compressor, I'm going to guess is mainly doing compressing. CLS, I don't know what that's about. Ceph admin is some administration stuff. Crypto, I will ignore for now. I don't know what Dokkan is. Or exporter. These are some, I guess, Git submodules. They're using Google test and format. I'm guessing that's some formatting tool. And we have Java, which did not appear in the list of languages, I don't think. Maybe it did, and it was just too small to notice. MGR is some manager. I don't know who actually speaks the Koorosh. OSD, we want OSD-C, maybe controller, OSD controller. Perfglue. Power DNS. This is maybe some DNS implementation. Telemetry tools, tracing, and other stuff. What's down here? Many more things. Ceph OSD CC. Yeah, I guess let's look at that. We can ignore Ceph ver. I'm assuming that's version. And we have, in the README, we just have one guy. Sage Weil at newdream.net. Okay. Here's cephcrash.in. Now, what do we want? RocksDB is like a distributed, not distributed, I think specifically non-distributed, but it's like a key value store like LevelDB or BerkeleyDB. I think it's a fork of LevelDB from Facebook. RGW is the object storage. Should I open it? I don't know. RBD replay. This may be for replay testing or something. And OS is, I'm going to guess, operating system specific stuff. Journal might be important, but who knows? Global and include, those could be promising. Erasure code, that's going to be some erasure code implementation. I don't think we need to look at the implementation. I don't know what Crimson is, but Koorosh we already opened. And Common might have some important stuff in it. Did I open class? I think I did. All right, so let's take a look at these. Oh, BLK is probably block storage. And auth, I guess I'm mostly going to ignore. So Koorosh doesn't have many things here. We have Koorosh compiler. I'm guessing that's for eating the Koorosh rules and compiling them. And we have Koorosh tester, Koorosh wrapper, builder. I don't know what we are building. And then Koorosh.h and Koorosh.c might have the most important types in them. Although we have types.h and hash.h. And grammar. This is presumably the grammar for just defining the Koorosh rules. I don't know why they define their own stuff and not using an existing config language, like say YAML. At any rate, let's look quickly at the grammar. And these look like the types of things you can be, like a positive int, an integer, a name, a device, a step choose, a choose leaf, etc. And we've got boost spirit. Is that a parser? Boost spirit, what are you? Object-oriented, recursive descent parser. Okay, so that's some parser, and we're using it, and we're parsing tags and stuff. Devices, we're going to get the device. Blah, blah, blah. Tunables. This is interesting syntax. It's very readable, but I don't know what it does. I mean, the strings are readable, but I don't really know what it does. We're taking bucket type to be equal to the whatever string strp is of type. Piping that into, not piping, but like right shifting operator, like this is also like the stream into the posint and stream into name. And this is, these are presumably operators overloaded by Spirit, and I'm not quite sure how to read them, but it's something about parsing. Here's hash, and the hash header just has Koorosh hash 32. These are some 32-bit hashes, I'm guessing. Types. Types has not much. You've got bug on and not bug on. Okay, so like including for integer types. That takes us to mapper. Let's go to crush.h, see if we can find it. Where are you? Here you are. And crush.h is not big, I don't think. Where's our lines of code? Do we not get it? 556. Hello, I have spawned. Hello, bot eater. Are you a bot? I like the disco. Welcome. It's good to see you. I'm glad you're hanging out. All right, so Crush is a pseudo-random data distribution algorithm. So most things are pseudo-random. It's hard to find truly random, but I think that what this means is it probably takes some sort of seed and distributes things, but not randomly, because you need to be able to figure out where things are when you retrieve them. I assume is what's going on, but we'll see. That efficiently distributes input values, typically data objects, across a heterogeneous structured storage cluster. The algorithm was originally described in detail in this paper, although it's evolved somewhat. So this is the while. Is Sage While the guy that we saw in the other README? This is presumably the paper summoned by C++. Oh, I didn't know that was your the magical incantation that summoned you. Are you a C++ dev, bot eater? I don't remember if I've ever asked you what your main language is. I like the Clippy. I don't know if UCSC wants to give me this paper. Why do I keep opening history? Maybe here? Assets PDF. Okay, here. Sage A. Weil, Scott A. Brandt, Ethan Miller, and Carlos Maltzahn. All right, so here's the algorithm. It's 12 pages. You can read it. It's got this thing. This is like pseudocode. Crush placement. Procedure. Put item A in working vector I. Okay, and procedure. And then select n items of type T. And we've got some for loops. Retry descent. No failures yet. Loop over the n replicas. And start descent at bucket I. I don't know exactly how we're descending, but that's something. Here's a simple rule that distributes 3 replicas across 3 cabinets in the same row. And I'm not sure if this is actual syntax. We'll say take root, I guess returns the root, select 1 row, I guess returns row 2. Seems like maybe we're indexing by 0 here and 1 by here. I don't know. Select 3 cabinet. Oh, maybe this is just saying get a single row as opposed to one particular row. This says select 3 cabinet, and it gives us cabinet 2, 1, cabinet 2, 3, and cabinet 2, 4. And you're selecting 1 disk from each cabinet, I assume, and then emit. Okay. Collisions, failure, and overhead. So I don't know what a row is. So often the cabinets are stacked horizontally. I don't know if a row is like a slice across several like clusters or something. A partial view of a 4-cluster map hierarchy consisting of rows, cabinets is maybe what I meant, not cluster, and shelves of disks. Bold lines illustrate items selected by each select operation in the placement rule, and a fictitious mapping described in table 1. And okay, so we have root. You're going to choose a row. I think here you chose rows 2. This is probably the same rule. And then we're selecting 3 cabinets, these 3, and then selecting 1 disk on each of the cabinets. Okay. But how does it select? List buckets, evaluation, straw buckets, overload protection, variance, and partial failure. So maybe the way it selects is whoa. Maybe the way it selects is described completely by the algorithm. this is some speed of the different operations. So whatever uniform is, list, tree, and straw. Oh, maybe straw is straw buckets. List and tree buckets are structured such that the limited number of hash values need to be calculated, etc. Okay, so I guess these are different ways of structuring the buckets. So how do we... It's designed to distribute the data uniformly among weighted devices and maintain statistical balancing. But how does it do that? How does it get the statistical property? Maybe we'll look for the word random. Pseudo-random hash-like function. But what are we hashing? Okay, given a crush input value of X and a replica number R, we choose an item from a uniform bucket of size M using the function C of Rx. I'm guessing C is for crush. Crush of Rx is equal to the hash of X. We're going to hash the input and add R times P mod M, where P is a randomly but deterministically chosen prime number greater than M. And what is M? M is defined somewhere. I don't think it's here. Oh, okay. Bucket is the bucket size. So R is some prime number bigger than M. So that, yeah. So that the mod M works. And then P is what? I don't know. I don't know what P is. Do we get, what happens if I highlight all the P's? Where did it go? Here. Where P, oh, P is the prime. What is R? Oh, R is the replica number. Okay. P makes more sense as a prime. So we're hashing the input and adding the replica number times a prime, taking that modulo M, where M is the bucket size. This is for uniform buckets. And then for tree buckets, maybe we do something different. Something about hashes. But it's presumably similar. We're some function of the hash, the bucket size, and whatever R was. No, I've completely forgotten what R was. Let's look for prime. Hello. Hello, prime. The prime number theorem for arithmetic progressions. Yeah, so P is the prime number, R is the replica number, X is this thing, and M is bucket size. I forget what I was even looking up. So P is the random one, but strange how you look up the value next time. What do you mean by TID? Oh, what do you mean by THID? If this is if you mean this, how do you look up the value next time? So to look up the value, you know the bucket size, I assume by looking up into some map. R, okay. Sounds good. R is the replica number, which I think is maybe also looked up in a map. And the prime, I think, is fixed. It says deterministic. I don't know if it is like the same for every Ceph, like for a fixed Ceph installation, like version 2 uses just one particular prime. That I don't know. And then we are just hashing the input. So when we have the input, I think these other two are fixed for the cluster that you're working in. So the main thing is hashing the input, and then why not just choose it based on the hash? Well, we need to take mod M because if you have like, let's say your bucket is size 4, you're choosing a bucket. No, you're choosing an item in the bucket. So you can't choose like item 5. It has to be less than or equal to M. That's what mod gives us. I don't really know how P is chosen, but maybe we will see it. And I don't understand why not just take the hash. There must be a reason that has to do with the replica count and not wanting collisions. In fact, there's a section on collision. And it sounds like we're... the select NT result must be distinct if a device is failed or if a device is overloaded. Failed or overloaded devices are marked in such a cluster map, but left in the hierarchy to avoid unnecessary shifting of data. Okay, so there's some retry for closing. I will read the whole paper later. I don't know if it will successfully save the Walla bag because it's a PDF, but that's usually a crapshoot. All right, so that's the paper. That gives us a little bit of intuition. In fact, I probably shouldn't delete it. Let's keep it up here in the background. No, not this one. How do I do it? Tab. No, it's not going to do it. We'll have to look it up again. Okay. So we have a crush rule step and whatever. This is some, I guess, an op and 2 args. We saw some of the operations, I think, in the paper. And we have op codes. Do nothing. This is, I think, supposed to be a comment on no op. But we have the take rule and the choose first, choose IDEP, INDEP, maybe independently. You can emit the rule. We saw in the paper that emit was basically called at the end to say the rule was done. We're done and like compile it or whatever. Set choose tries. I don't know if this is the number of like retries or if it's try in the sense of a tree. I'm guessing this is like retries. And then descending. I didn't really read the part of the paper where it talks about descending. I don't know exactly how they're descending or why, but maybe we'll look that up. Then a crush rule is a struct that has some length. Unused was rule mask rule set. What? Oh, I guess this is something that used to be in the struct and is now currently unused, as opposed to a part of the rule that is like unused in your cluster so far. That was my first thought. I think this is basically part of the code that they've obsoleted. And then a min size and a max size, which are also deprecated. So like 3/5 of the struct seems like is no longer used. Maybe that's an optimization. And we have some crush rule size, crush rule type replicated, erasure, MSR first and MSR in-depth. I don't know what MSR is. Erasure is some erasure coding thing. A bucket is a named container of other items, either devices or other buckets. Okay. So maybe that's part of what the recursion is that once you choose a bucket, you have to choose within the bucket. And so I guess you maybe you're putting some object. I guess you like hash the object or something. And then you, or first it's like broken up. So I'm assuming the thing they hash is a small thing. And so on the outer layer, you get, I guess, which bucket it's going to go into. And then that's also a bucket. So you look inside of it to get what? Like a device eventually. Maybe it's like 4 layers of buckets before you get to a device, depending on your structure. Items within a bucket are chosen with crush do rule, using one of 3 algorithms representing a trade-off between performance and reorganization efficiency. If you're unsure which bucket type to use, we recommend using Ceph bucket straw 2. And this is the speed. This is also from the paper. Here's the enum crush algorithm. Devices are rarely added individually in a large system. Instead, new storage is typically deployed in blocks of identical devices, often as an additional shelf in a server rack, or perhaps an entire cabinet. So an additional shelf. and a server rack. So the rack is the physical cabinety thing, I think. I don't know the difference between a rack and a cabinet, but a shelf is a shelf. And because disks are smaller than machines, to make a disk thing the size of machines, you typically have many disks. Rack versus cabinet server. In fact, the main difference between a cabinet and a rack is that racks are open and have no sidewalls, while cabinets are closed on all sides. Oh, okay, I didn't know that. A rack looks like this. A cabinet, I guess, has some... Here we go. This is the difference. Okay. This one's just closed. Otherwise, they're the same. And then a disk is like an array of disks because it has to take up the same physical space as a server. And I didn't realize they were like this. The ones that I've used, I think were all horizontal. So this makes more sense, the rows and the columns. So once you pick a particular machine, you have some number of rows and columns of disk. And that's why I was confused before. Okay, cool. So the documentation is saying you typically, so this is one unit. Typically you would stack, I don't know, whatever it is, 10, 5, 8 of these units into a cabinet. And that's the size at which data devices are added to a cluster in a big installation, like at a big company. Okay, devices reaching their end of life are often similarly decommissioned as a set, individual failures aside. Okay, so a disk fails, I think the disk is just typically replaced. But if they're all like 9 years old or whatever, you might just replace the whole rack, making it natural to treat them as a unit. Crush uniform buckets are used to represent an identical set of devices in such circumstances. So a uniform bucket means I think all the devices are exactly the same. So they have the same storage capacity. They're all however many terabytes, and they are made probably by the same manufacturer, the same speed, all that stuff. It can map the blah blah into uniform buckets in constant time, maybe as opposed to like if you had a heterogeneous array of like 1 terabyte drive, a 500 gigabyte drive, and a 40 gigabyte drive. It would Ceph would have to reason about how to distribute the load in those different buckets with the different considerations of like not wanting to fill up the disk, but also wanting to have the right number of replicas. In cases where uniformity restrictions are not appropriate, other bucket types can be used. Okay, so that's the uniform bucket. And then what is down here? List buckets structure their contents as a linked list and can contain items with arbitrary weights. Okay, so the weights, I guess, are to just express the fact that they're different, possibly different capacities. To place a replica, Crush begins at the head of the list with the most recently added item. Okay, and compares its weight to the sum of all remaining items' weights. Depending on the value of hash XR item, this hash is now different. I don't know if it just, they made it simpler or something. Either the current item is chosen with the appropriate probability, or the process continues recursively down the list with the appropriate probability. Okay, I don't know how that appropriate probability is chosen. This is natural and intuitive for an expanding cluster. Why? Either an object is relocated to the newest device with some appropriate probability, or it remains on the older devices as before. The result is optimal data migration when items are added to the bucket. Is that so? And then a bucket straw is a straw bucket. List and tree buckets are structured such that a limited number of hash values need to be calculated and compared to the weights in order to select the bucket item. In doing so, they divide and conquer in a way that either gives certain items precedence, for example, those at the beginning of a list, or obviates the need to consider entire subtrees. The straw 2 bucket allows all items to fairly compete against each other for replica placement through a process analogous to a draw of straws. So there's suboptimal reorganization behavior when the contents of a bucket change due to an addition. Okay. So let's ask, now we're at a place I think we should ask, I think Gemini is having an outage. Come on, Gemini. Let's ask ChatGPT in the crush algorithm, how is the hash computed for uniform buckets? Answer succinctly. Okay, we're taking, all equally weighted. The hash is computed as H is hash of input R mod n. The input is the placement seed, usually the object ID plus the replica index. So it's the object ID. R is a retry counter, and n is the number of items in the bucket. Okay, so how do you get the object ID? Is it stored with the object? So how does fetch work? It's not stored in the crush map or the placement groups. It comes from the client side. Every object in Ceph has a unique ID. The client hashes that name to determine. So how does the client know which object ID it wants to fetch? I guess it has to be stored like in the layer above. It's the identifier of the application used when storing the object in the first place. It gives, so when you write data, it gives Ceph an object name. So are these like UIDs? They're generated by the higher layers. You can directly name objects with any string. For example, my object 123. Object IDs are derived from the file. Okay. Okay, what about in RGW? Okay, so you have some bucket and some thing like a cat PNG. And then large objects are split into multiple Rados objects with just some name. Okay, so that's the object ID. It's basically any string. Okay, that's fine. And so you're hashing the ID and not the content, which is what I thought you were doing. So where's the hash function? So you're hashing the object ID and the replica index. What is the replica index? Or is the client choosing which replica to fetch? Is a counter telling Crush which copy of the placement you want. Okay. The primary, secondary, and the client wants to place or locate an object. It runs Crush multiple times with replica 0, 1 up to the pool's replication factor. Okay. Normally the client doesn't pick blindly. It asks the primary OSD for the object. It asks for the... Okay, so normally you ask for replica 1. That seems like that's not the best performance, but that's okay. And then you may redirect to secondaries, etc. Okay, and then I mean, you never know if ChatGPT is actually correct that this is the formula, but so the input with the replica. Okay, that gives us a hash. And then what is R? It's a retry counter. So is the retry counter, that may be mainly for dealing with collisions. To handle cases where the first hash choice isn't valid. So you hash to pick a bucket, say OSD, might be down or out of the pool. Okay. Great. And then so I thought there was a prime number. In the paper. Okay. This is pretty close to what it said. So it kind of moves that. Yeah. Yeah, that's right. So It kind of moves the hash. I mean, that's really all you can do with hash. Is you're going to change the you're taking a hash and mapping that into a list from the set 0, like say 1, 2, 3, 4. Let's say that you have 4 things, n is 4, and when you change the like replica, the retry counter, you're like adding 0 to the end of your input, or 1 or 2 or 3. And then because it's a hash, that's going to map kind of like arbitrarily to some other element of the 32-bit space, assuming this is a 32-bit hash. And then you're going to take the mod end of that. And so that's going to, most of the time, pick another number. But if n is 4, you don't have like a lot of play. There's only 4 numbers to pick. Okay. So all that's good. That makes sense to me. And it seems like the client has to be relatively smart. And okay. And then there's this stuff about straw and trees that I'm guessing that that's just going to be different flavors of the same stuff. Maybe we should ask. Okay, so how are the hashes in tree and straw buckets? I don't know I don't remember if it's a bucket property or a property above them. Okay, so in the tree, each item has a weight. Similar with the list, the bucket is organized like a binary tree. So Koorosh computes a hash at each decision point or node to choose left versus right. So I'm guessing they do some hash that probably depends on the input. It may depend on like which row you are in, because that's uniquely defined for the binary tree. And then you're going to like hash it mod 2, I guess, to choose left or right. After a sequence of hashes down the tree, you land on one weighted item. The weight needs to go in there somewhere. And then for straw bucket, each item has a weight. For a given object, replica, index, retry, Koorosh computes a hash per item. Each item's hash is scaled by its weight, producing a draw length. The item with the longest straw wins. Okay. Give me the exact formulae. Bot Eater's wondering if one could use this technique to replace linked lists in dictionaries. That would require storing the ID with the object. In dictionaries. 90 moon vibes. Hello. And by linked list in dictionary, do you mean the like when there's a collision, there's usually a linked list, I think, to resolve hash collisions? And by dictionary, do you mean hash map? If so, then maybe you're asking, can you rehash it by like appending something to it to resolve the collision? Yeah. I guess you could. Although it's probably slower because the hash is usually slow to compute. But I can ask if that's a thing. Uniform bucket, all items are the same weight. Wait, hey, now we have the P again. In a tree bucket, left if hash XR mod. Oh, so we have the weight of the 2 children. This, I'm guessing this is just the Boolean. You're going to check if the... Stop it. The W left plus W right is less than... No, it's this. This is the clause. You're going to take the hash XR mod, the sum of the left and right, and check whether that's smaller than the left. So that's not... You're not modding by 2. I don't really know why this is the right thing to do. I guess the weights give you something like the bucket count. Okay, and then a straw bucket, we're going to take the negative log of some hash of XR and J over 2 to the 32nd. And we're going to divide it by the item's weight. And the winner is the argmax. Okay. In designing a hash map, are there designs that on collision append something to the key and rehash it instead of using a linked list to handle collisions? It's called opening. It's essentially open addressing with key transformation. Chaining is the linked list approach. Open addressing, all entries live in the hash table itself. Collisions are resolved by probing for alternative positions. The idea of append something is conceptually similar to rehashing and open addressing. There are a few canonical ways to do this. So you have hash of key collides. Try hash of key plus one. Okay. Key isn't modified per se, but yeah, right. That's a fancy, open addressing. By the way, I have the dark theme on. I don't know why. I don't know why it keeps dark. I don't know why Firefox keeps giving me this light top. Open addressing or closed hashing is a method of collision resolution in hash tables. Hash collision is resolved by probing or searching through alternative locations in the array. There's linear probing, in which the interval between the probes is fixed, often set to 1. Quadratic probing. But how do you actually probe? Find slot. While slot I is occupied and slot I of key is not equal to key, I is defined to be I plus 1. Find slot. Okay, so here we're just hashing. And we're not rehashing at all. We're just like, if your cubby hole is occupied, just take the next one next to you. And then quadratic probing. The interval increases linearly. So if the next one is occupied, try the one 2 away. If that's occupied, try the one 4 away. Is maybe what it's saying, although I don't know. And then double hashing, in which the interval is fixed, but each record is computed by another hash function. That's what you're talking about, I think. What I described as quadratic would be, I think, in fact, exponential. But the interval between probes increases linearly. Let's see what this is. So you're going to take the hash. This is more complicated. I'm not going to look at it. But I think double hashing is a conjunction with open addressing in hash tables to resolve hash collisions by using a secondary hash. And so if I were, so let's go back to this history. Wait, where? Library? Is it library? Oh, there's Kafka. Where's my history? Here we go. I've hit the limit. What is this related to open hashing with, what is it called? Rehashing? With double hashing. Arguably, it's basically the same thing. Is that calculus? Is what I don't think anything was calculus. There was some like finite math. There might have been. I think just algebra. There might have been a derivative or an integral. Double bashing. Double bashing is also good. Not directly, although there's a superficial similarity. Okay. Yes, make the world's most complicated and pedantic diagram. I need it for my presentation tomorrow, and I absolutely have to be promoted. The management loves complicated diagrams. see what you do with that, Chat GPT. Okay, so that's a bit about Crush. We should see the hash functions here. They're pressed as sponsors or managers. Yeah, exactly. So this is basically the same. We're going to hash XR and item, where maybe item is the item's index or the weight and something. But anyway, these are just the enum values. We can maybe see the implementation. Crush, destroy, bucket tree. Crush, destroy. Destroy a crush map. So this is destroying the actual map. Wait, I don't know. It says we're calling crush destroy bucket. I don't know where the actual hashing is. It doesn't seem to be in crush.c. Mapper, I think maybe this is an ASCII diagram. Annotations in pedantic. Yes, turn it into a visual. Yes, turn it into a visual diagram with colors, arrows, and object weights. Nice. This is our corporate color scheme. Make them 4D. I don't know if ChatGPT has that power to make something four-dimensional. It takes it a while to render. I'm assuming I'm going into some queue with all the rest of the ChatGPT users. Okay, crush do rule is in Mapper. So what is Mapper? The in-group API. Map X to result max items and store them in the result array. The mapping is done by following each step of the rule. Rule no. See crush make rule, blah, blah, blah. The return value is the number of items in the result array. So this is, I think, just kind of like the do function for applying the rule. And maybe this might be where hashing happens, but it may not be. Yeah, bucket perm choose. Choose bucket based on a random permutation of the bucket. We used to use some prime number arithmetic to do this. Sounds like the prime number is gone, but it wasn't very random and had some other bad properties. Instead, we calculate an actual random permutation of the bucket members. Since this is expensive, we optimize for the R equals 0 case, which captures the vast majority of calls. And I think this is maybe because R equals 0 is used for fetch. And it's also like you almost always put it there. I'm not sure. Yeah, calculating a random permutation is kind of insane. Is this why it uses so much of my CPU? Why don't they pre-calculate all the random permutations? 32 bits. Why don't they use like some sort of rainbow table? Maybe they do. We'll see. But let's see if this diagram is there. No, still working on it. But we're almost done. Not quite. Okay, so we have some bucket size. We're going to take R, which I'm not really sure what it is. Maybe the replica count, and take it, get it modulo the bucket size. That's going to give us a PR, and we've got I and S. Start a new permutation if @x has changed. I'm assuming @x is just the documentation reference for x. So whatever work is, there's a work bucket. I don't know what a work bucket is. So work at permutation x is not equal to x cast as a 32, uint 32, or work perm n is equal to 0. Then we've got some debug print statement. We'll set work perm x to equal x. And then here's the optimized case for R equals 0. If PR is equal to 0, we'll take the crush hash 32.3. I'm guessing 32-bit hash crush because it's the like a local version, as opposed to like a upstream boost hash map. And 3, I assume, because it takes 3 arguments. And we're passing in the bucket hash X and the bucket ID and 0 being, I think, the replica account. And taking a modulo bucket size. We're setting work perm of 0 to be S. Okay, so the permutation of 0 is set to be the S, the hash. And then the work perm of N is some magic value of all Fs. And then we're going to go through out. Otherwise, for each element in the bucket, we're going to set work perm of I to I. And then work perm of N to 0. We're still in the special case, I think. No, we're not. This is the end of the special case. I'm not sure why we're sending all of the permutations of I to I, or what work perm of N is 0 meaning. And then if we're here, this is the magic value. Clean up after the R equals 0 case. We're going to reset the permutations. And this calculates some permutation up to PR. Okay. So that's kind of crazy. It's just doing some permutation stuff. I guess I don't... this may be obvious. It's been a while since I've written a permutation algorithm, but it seems like if you already know what I is, enough to index into the permutation, then... I mean, this is the identity permutation, right? There's heaps algorithm. This is doing some swapping. So let's, I mean, am I missing something? Let's ask chat, that's DeepSeek. And this, I'll go, why is the permutation setting perm at I equals I? Is that the identity permutation? I'm not gonna respell it. All right, this is pretty good. Key object photo cat.pmg crush deterministic hashing retry counter. We got the deterministic hashing here. Okay. It's pretty good. Add a cat in the corner. And add some more boxes, even if they don't clarify the point. Okay, it's not letting me do that. Fine. So for here, yes, I've got it. The identity permutation is the permutation that leaves everything in its original order. This is a do nothing permutation. Why is this so common? Initializing to the identity permutation is fundamental and safe starting point for many algorithms. So maybe it's just initialization, but aren't we kind of close? Maybe not really close. Maybe we're not close to the end. Calculate the permutation up to PR, while some stuff unsigned, blah, blah, blah. If bucket size, blah, 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 blah. Okay, so I guess maybe they are doing more work. It's kind of insane that they are doing this. Try now. No, I'll try later. So in the current crush implementation of Ceph, they have switched to computing permutations. I think they're random permutations in mapper.c. Is this optimal performance? can they achieve better performance with the same design requirements by pre-computing parts of permutations? Or are they already doing that? All right. I'm not going to look anymore at mapper. I don't know what build is. Builder is allocate a crush map with malloc 3 and initialize it. The caller is responsible for deallocating it. Analyze the content of map and set internal values required before it can be used. So I think this is about building crush maps. And then crush compiler is, we saw the grammar. This is for turning the rule into like opcodes and stuff. I think that's about all I want to see with crush. Modulo, seeing why they're doing this permutation stuff. And that's most of what I want to see. Maybe I'll take a look at some of the stuff where they write physically to disk, but we'll like look at least briefly at these other things I've opened. CLS, I have no idea. CLs. We have FIFO, which is some Q stuff, I guess. There's a lock, a journal, hello. Class.hello. A simple Rados class designed to be usable as a template for implementing new methods. So now we're getting to the Rados stuff as opposed to the crush stuff. Actually, we should look at Rados for sure. Say hello is a read method that does not depend on the object. So you've got a class method context, some like, I guess, context, a buffer list of input and a buffer list of output. And we're just going to append hello to the output, I guess. Okay. And then what is CAS? CAS client. Chunk read ref count. So this is some of the implementation. We have a client header. Copy something. Create a chunk or get additional reference if it already exists. So CAS chunk create or get ref. You give it some write operation from librados and an SOID, something ID. I don't know what S stands for, and a buffer, and don't verify it. Okay, so these are somehow used to make different implementations. Okay, so here's RGW, and maybe we can look at the ops. We have encode, encode start, encode, decode finish. Write class encoder. With this RGW class obj prepare op. RGW modify op. And, I think that what this is doing is encoding stuff to be consistent with the S3 API. We have like a tag, a locator, a key, a bylog flags, and zones trace. I don't know what that means. Maybe zones trace is about like availability zones, like something about where the physical representations of the data are. If you have an S3 style like region or something, I don't know. I'm just guessing. But at any rate, we have all these encode things, and we've got some Ceph bucket things, and this is just kind of too complicated and too much stuff to really dig into unless I have a specific thing I'm looking for. But we'll just do like a tourist look through RGW, SDK. It's not much here. Test storage right. Maybe, okay. Here's Ceph FS. We have a client and there's not much here in Ceph FS, unless this is not the whole implementation. We've got an object ceiling. It's a value class for the X adder that we'll use to accumulate the highest object seen for a given node, etc. And some accumulate args, etc. So let's see if we can find another Ceph FS directory. Because I'm not sure. Wait, what? Yeah, okay. Here's a Python dashboard controller thing. That's, I guess, for the UI. I don't know what MDS CephFS features is. Here's some CephFS tools, some more Python bindings. I don't know where the main implementation of CephFS is. More Python, more Python. What about RGW? Okay, so RGW gets its own top-level source thing. And is the same true of CephFS? I don't know. Seems not to be. But I'm not sure. I'm not going to look too much into it. I have no idea what Dokkan is. Maybe some debugging thing. Manager is something about managing the state of the cluster. We've got some Pi stuff, like Pi formatter, Pi module, some perf stuff. I guess we can kind of guess what this has to do. So like you have the crush stuff. There has to be some entity that's receiving API calls and doing crush. In fact, if you have three Ceph servers, the fact that they use the crush maps means they can all do crush independently. I don't know quite how the requests are distributed to the different servers, how to make sure that they don't all write or receive the same object, but that must be that must be done somehow. I'm not sure if that's what the manager does or if that's what something else does. So Ceph manager. Ceph manager daemon. It runs alongside monitor daemons to provide additional monitoring and interfaces to external monitoring and management systems. Okay. So the writing orchestrator plugin. In this context, orchestrator refers to some external service that provides the ability to discover devices and create Ceph services. This includes external projects such as Rook. Rook is a way to configure like a Kubernetes cluster to use Ceph. I don't know if the requests go directly to the OSDs. We have daemons and services, orchestrator service, etc., and devices. Let's ask. I guess this one is not capped out. In Ceph, where do read and write requests get sent initially? Who is serving the API? Is it the OSDs or some other server or daemon? It is an excellent question. Thank you. So they're sent to the cephmons, okay, for cluster mapping, and then directly to the OSDs. So let's look up cephmon. Is the cluster monitor daemon. One or more instances of cephmon form a Paxos part-time parliament cluster. Okay, so they speak Paxos to each other, so that gives them a leader that provides extremely reliable and durable storage of cluster membership. Okay. They have a keyring, they have a group. How about Ceph data flow? I guess for like RGW, the requests go directly into the Rados gateway. I feel like we haven't really seen Rados yet. So storing data, there's an object, it goes on an OSD. The OSD basically controls a drive or maybe runs on a drive. The Ceph OSD daemons store data as objects in a flat namespace. I don't know if the OSD, I don't know if there's like, we saw those disk clusters. I don't know if one disk cluster has one OSD or how they normally do it. Not like this. More like this. Like, I don't know if one of these has as a single OSD or if there are multiple. But where do the monitors fit in? So you have multiple monitors. The monitor map contains the cluster FSID, the position, the name, the address, and the TCP port of each monitor. The monitor map specifies the current epoch, the time of the monitor's map's creation, and the time of the monitor map's last modification. I am losing my voice. Why? All right, so DeepSeek is claiming that the initial connection goes to the monitors, and then there's client-side computation of the Crush algorithm. The client uses the Crush algorithm locally to calculate where data should go. So is that right? So is the client doing it? Then why does Ceph use so much CPU? And then there are placement groups, which we haven't seen yet. And then which OSDs store that placement group. And then the direct OSD, the client communicates directly with OSDs for actual data operations. Okay, so the client is communicating with the OSDs. Why does Ceph use so much CPU? Hello, VibeForge. You're the second Vibe. Wait, are you the same Vibe user? Is that calculus? So there was some Vibe person here before. Are you the same person, renamed? VibeForge. The Koorosh algorithm complexity, blah, 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 blah. Data path processing. Checksums, replication logic, erasure coding. But if the Koorosh algo is done client side, why would the why would that cause CPU usage on the server? All right, you're too verbose. Stop it. Let's see how Gemini is doing, asking about random permutations. The current Crush implementation is highly optimized for specific design requirements. It may not be optimal, blah, blah, blah. It provides a deterministic and stateless method, blah, blah, blah. The use of a stronger hash function is the key to this process. Pre-computing permutations or parts of permutations would fundamentally change the nature of the Ceph algorithm. It would introduce a new layer of metadata that would need to be stored, managed, and distributed to all clients and OSDs. An increased metadata overhead, slower rebalancing. So the Koorosh map itself can be considered a form of pre-computed data. They're always done on the fly. I'm not sure. What are the permutations? Are they essentially elements of the permutation group on 32 elements? Or what number of elements are we talking about? Is it just the number of like buckets or something? Okay. And then you're absolutely right to question this. I oversee it. Everyone uses the same terminology. I don't know where this is coming from, but these LLMs are obviously copying each other. I overstated the client-side Crush impact on servers. Data path processing. I'm not sure. Like checksums, replication coordination, erasure coding, massive CPU consumer. If using EC, the CPU cost is enormous because of the erasure coding. Maybe. I don't know. Permutations are not elements of a formal permutation group. Instead, they are pseudo-random deterministic orderings of the object storage devices within a given bucket. generates a unique but repeatable ordered list of OSDs within a specific bucket. This ordered list is the permutation. Ceph then selects the required number of OSDs from the top of this list to store the replica. Pseudo-random deterministic orderings of the OSDs. The number of elements in these permutations is not a fixed number like 32. It directly corresponds to the number of items, which can be OSDs or other nested buckets within the specific bucket. It corresponds to the number of items, and it's dependent, stored in the bucket. Oh, no, okay. Not like items as an object. It depends on the number of OSDs and other things. So that's relatively constant. So how are the permutations actually calculated? What's the... Are they pseudo-random? I think they said they were deterministic, right? What is the algorithm for making a pseudo-random deterministic permutation that Ceph uses? Check the hash32 function. I mean, we could look at the code. But I've lost where it is. It's in monitors dot something or other. I was finding their code not so easy to read. No, it wasn't monitor. It was map something. Mapper.c. We have a document. We have an RST document. Or we can also like Ceph permutation mapper. I don't know if this is going to have like the implementation details. Okay, so here's the mapper. Did I open also the RST doc? Maybe, but maybe in a different place. I don't know. Okay, so calculating the permutations up to PR, we are going to iterate over whatever perm n is. We don't know what work is, and we don't know what perm n is. Maybe we could just look for a Ceph work bucket. The blah, 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 blah. OSD work buckets. A third, more specific use is related to the quality of service. Buckets are actually traffic classification. This doesn't sound right. I don't know if I believe you, AI mode. Maybe that's the bucket we're working on. And what is perm n? Is it like the size of the permutation? Oh, here we go. There's a struct. Okay, so the crush work bucket is a struct that has the X for which the permutation is defined, the number of elements of perm that are permuted or defined in the permutation of the bucket's items. Okay. So I don't know what X is here. These data structures are private to the crush implementation. They are exposed in this header because the builder needs them. Okay. So we have some work bucket that is the thing that is like recording the permutations. That seems to be basically all it does. I don't know why it's a bucket. Maybe it's supposed to be like the bucket that we're working on. And maybe that's what X is supposed to be. we pass in bucket perm choose. We pass in the crush bucket and the work bucket. I don't know where this function is called. Let's do this in another thing. We'll ignore manager. So perm is presumably permutation as opposed to permanent. It's not like a permanent choice. Since this is expensive, we optimize the, okay, this is just the same function. Okay, fine. But where is it called? Here. 118. Bucket uniform choose. We pass in a bucket and a work bucket, and we just send it there. So where's bucket uniform choose? Or rather, who calls bucket uniform choose? That's what I want to know. I just want to know like how these are called. Zero more. Nobody calls it. What? Okay. Fine. Keep your secrets. All right. So we're calculating the permutations up to the pointer. So we have some perm n, that's like the maximum length of the permutations. Well, work perm n is less than or equal to PR, where PR is essentially the like replica size, the replica modulo the bucket size. Where did we go? Why, I don't know why perm n would be less than or equal to PR. But at any rate, we're going to set P and a new unsigned int P to be the perm n. No point in swapping the final entry. If P is less than the bucket size, -1. So it like fits into the bucket. We'll take the crush hash 32.3 of the bucket hash, X and the bucket ID P, modulo bucket size minus P. That gives us an index I. If I is, I guess, non-zero or non-null, then no point in swapping the final entry. So that's why the -1, I guess. Then we'll set T, the unsigned int T, to be the thing currently in permutation P plus I. So we have P is like the, was initially set to perm n. And then we're going to set perm at P plus I to be work perm at P. So we're swapping P with P plus I. And we are setting, so T is a temporary variable, and we're just swapping them. Okay, so that makes sense. Then we're just incrementing perm n plus plus. So I don't remember what perm n started as. Maybe it was set to 1 here. And we're just, I don't know why we're increasing perm n. I thought it was like the size of like the number of elements we were permuting, but there's kind of something else about it. It's growing as we do more permutation. And also the permutations are, they're not bound by perm n, they're bound by PR. So perm n is like an index in a sense. And it's just telling us where we're working on, I think. Here, yeah. So perm n is basically the same as P here. It's the element that we're actively swapping. Okay, so that makes sense. I guess there's not much really in the computing of the permutation. We are selecting an element of some permutation group implicitly. But the real thing we're doing is it's the hash that determines which elements are swapped. And you need to know, so even if you had like a map, even if you like named all the elements of the permutation group, to find out the name of the permutation you need, you'd have to know this hash essentially. So I guess that's why it doesn't work, but it's not clear to me why. It's not clear to me why you can't do something like just hash the two things without P and then look up a permutation for them and use them. Or like I don't know. I guess it doesn't matter. Gemini seems to think thinks it's a good implementation. So here's what it says about how it's done. Very fast integer hash function, blah, blah, blah. The core of the process is a hash function called hash32 rjenkins1. It's not cryptographic. It's designed for speed. And they use deterministic shuffling. Imagine you have a bucket, for example, a server rack. You need to pick one in a pseudo-random but repeatable way, gather the inputs. The process starts by collecting several pieces of information to feed into the hash function. Iterate and swap. The algorithm then performs a simple and efficient shuffle, similar in concept to Fisher-Yates shuffle, but made deterministic by the hash function. It starts with the end of the list of OSDs in the bucket and works its way backward. For the last item in the list, it calculates the hash during blah, 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 blah. So the information is the placement group, the replica number, and the item ID. So imagine you have a bucket with a list of OSDs and you need to pick one in a pseudo-random. Okay, so in this problem, suppose instead we have a pre-computed list of so the placement group ID is a unique identifier for the chunk of data you're trying to place. So I guess the problem is it depends on the placement group ID. With a list of OSDs. So suppose you have a pre-computed list of permutations in some table, and you look them up by hashing the input, the placement group, and the replica number. This gives you a single hash which indexes into the table of permutations. This means computing only one hash instead of iterated hashing. Why does this fail? I assume it doesn't work. I'm just kind of curious why you can't do that. Evaluating the idea's flaws, pinpointing the critical flaw. Assessing the update cost, examining the core contradictions. So they're saying something about updating. You have to keep it updated. It's an excellent question. Yeah, it is. Thank you. It gets to the very heart of why Koorosh is designed the way it is. It cannot handle dynamic cluster changes gracefully. It's designed for real-world storage where the clusters are constantly changing. The pre-computed table is now completely useless. I don't actually know how big 32 factorial is pretty big. Yeah, okay, that's fine. It seems like there's something in the design space that allows for more efficiency. I don't know what it is. Maybe it's nothing. Maybe the efficiency of Ceph is not really a problem because You could just continue to throw CPUs at it, or it will get faster in some other way. I was just a little bit, I don't know, it's just like a rabbit hole. One of those rabbit holes. And I think I'm basically done. There's so much to look at here that we can't, as I said at the beginning, we can't really get to it all. I don't know if we can find like a Rados directory that has like all the Radosy things. Rados may be the name of something that's like wider and spread out. I guess the moral of the story is if your problem is exponential, try guessing a bunch of times. That is a good, I mean, that's a good thing. Do you guys know about the probably prime tests? Miller-Rabin? I don't know if I haven't really thought about what the running time of a primality test is, but it's O of log n to the 6th. That's actually not so bad. But the probably prime test is a good test that you guess a bunch of things and see if, and you look at the result modulo n, where I think n is the thing you're testing. And then it gives you some probability that it's not prime. And this can be done very quickly. And then if you really need to prove it, you could do a full prime test. Okay, so we have these pi bindings to Rados, PXD, librados. Yeah, okay, so here's the include for librados. And we have the struct has a client and a cookie and an address. Hey, stop that. And that's locker T. What? Locker T? Like as in a lock or as in like a foot locker? We have an API like list object, object cursor. This is maybe some pointer into the object. Object iterator, forward iterator tag, etc. Seek hash position, get cursor. Okay, so this is really is looking like an API that you would maybe want to use as a programmer, or no longer in the world of like crush maps and choosing storage. We're like now listing objects. But again, these are not again, but these are the Ceph objects, which are smaller and fiddlier than like the S3 objects. The S3 is like a bucket and an object name and a region, maybe a zone. I don't really know how S3 does it, but that's the Rados objects are much more granular, is my understanding. What I want now is Rados.c or CC. I forget what their convention is. Service user Rados, Neo Rados. What is Neo Rados? What if we look for list objects in the language of C? C++? I think list object was one. Q list object name, H object at H. Maybe in common? I don't know. I'm not going to really dig too much in. Here's placement groups. We haven't really looked at placement groups. I have no idea what Crimson is. Crimson might be is the codename from Crimson OSD, which is the next generation Ceph OSD. Okay, and then there's some blue thing, Blue Store. Blue Store is a special purpose storage backend designed specifically for managing data on disk for Ceph OSD workloads. It's based on a decade of something or other. Based on a decade of experience of supporting and managing file store OSDs. Is Ceph really a decade old? I guess that's not so old. So it directly manages storage devices. So as in, like, you don't have a file system on the disk that you add to Ceph. It just has like a raw disk. Metadata management with RocksDB. And add full data and metadata checksumming. By default, all data and metadata written to Blue Store are protected by one or more checksums. Okay, so we could probably find BlueStore somewhere in here. OS BlueStore types. I guess it's in OS. Why? I don't know. But we have, for example, decode BlueStore extent ref map t. The BlueStore p extent, the physical extent. That's a file system-y thing. And I'm not really sure what they're doing. I'm not going to really go into it. This would be like a whole hour, I think, on its own, looking at how BlueStore writes files. But I think in a sense, it's like an implementation detail. I think you could have, I think you can have Ceph write to file systems that are not BlueStore. I think BlueStore is like an optimization. What's going on is we're looking at the Ceph code and trying to kind of figure out a little bit about it. I don't know if we're succeeding. We've certainly learned a little bit. But now what I want to do before I go is draw a picture. Where's the banana one? So draw a picture. I liked in the documentation it mentioned the manager daemon. Manager daemon. How do you spell cephalopod? Cephalopod. Cephalopod. I got it correct, right? It should be a cephalopod manager daemon. And it will slowly generate. It's not bad. It's got like some sort of iPad, but the iPad is pointed to the user. And his name is Balfagar or something. Pretty good. Make it more demonic. The sort of thing you think of when you're having a bad day. So I guess that's Ceph. At least that's the scratching the surface of Ceph. Oh, you can't make things like that? What? Just make it, can you make it more, HP Lovecraft E, it's for Halloween. It's such a big project that I didn't think we were really going to get anywhere with it. We saw a bit of the crush mapping. I have a better understanding now of how it works. All of the other stuff, you can kind of figure out what those layers need to do. That's different from understanding how the code works or how you would debug it or whatever. But I think, at least to me, the other layers make a bit more sense. And that's, I think, all we've got time for. And here's a manager daemon. That's pretty good. And that is it. I'll see you next time on Answer Everywhere.